All right, so I'm going to repeat something that we did in class, and we're going to repeat it because it's really important. And it's very simple to derive here, but it is important, and it is the energy density in an electric field. So if we know a capacitor stores energy, and we know that it does because we determined this a couple different ways now, but Q squared over C. That's the amount of energy in a capacitor. Well, what is in that capacitor? In that space between the capacitor, there is an electric field. So another way we can think of this is that the energy here is being stored in the electric field. This is going to be really important when in a few weeks we will discover that there are alternate ways to make electric fields. So far I told you, anytime you have an electric field, you have excess charge. Anytime you have excess charge, you have an electric field. They're just the same thing. That's true, but it turns out that there is one other way we can also make an electric field. And I'm not going to get into it right now, but what we will discover is that there's an alternate method, and that electric field can also store energy, and that's a really important thing. It's behind modern civilization. So we know that this is the energy density in a capacitor, but let's just play around with the math a little bit, and I'm just going to use the fact that Q is equal to CV, and remember this is just from the definition of C, that Q equals CV. So I'm just going to replace that up here, and so what I have is 1/2 CV squared over C, and I'm going to say that this is 1/2 CV squared. So as long as we're here, I will mention this is also a very useful formula to have for the energy that's stored in a capacitor. It's just this exact formula, it's just a different formulation of it, so it doesn't need to be proved, but sometimes it's more convenient because you have these terms where you might not necessarily have other terms. So basically, you can see with the voltage here, you never need to calculate what the charge is on the capacitor. You can determine how much energy is stored just with this formula right here. Okay, but we're going to move on from there, because what we're going to say is we know what V is. We know V is E times D, and this is just, remember, that's just from the definition of potential. It's minus change in voltage over change in position. So voltage equals E times D, because V over D equals E, right? Okay, so this is just from definition, and now I'm just going to substitute this in here, and we're going to have 1/2 CV squared now becomes CE squared D squared. All right? But now, what else do we know about C? We know that C is also equal to, and I'm talking about our two plates once again, that C is equal to epsilon 0 A over D. So we're going to have 1/2 epsilon 0 A over D E squared D squared. And this now, remember, this is all what is the energy stored in a capacitor. Well, now what's this? Let's simplify this just a little bit more. So now we have 1/2 epsilon 0 A times D times E squared. Okay, so this is now a new expression for the energy stored in a capacitor. But let's take a look at this. What is A times D? A times D is, you will recall that A is just the area of our capacitor, and D is just the distance between those two plates. So, if we have this, we have these two plates, and they each have an area A, and the distance between them is D, then what is A times D? It is this entire volume, right? This entire volume. So the volume of a capacitor is just AD, and this equals volume. And so another way of thinking about this is we could say this equals Yeah, I'm going to go ahead and erase this right here. Okay, another way of thinking about this is we can say this is 1/2 epsilon 0 E squared times the volume. And then we say this equals the energy. Well, then the question is, what is the energy per unit volume? So we're just going to divide both sides by V. So we have the energy per volume. And now, what is anything per volume? If this was charge per volume, if it was mass per volume, it's density. So this is an energy density. Energy density. And this expression right here, 1/2 epsilon 0 E squared, is the energy density. It is the energy contained in an electric field. And it doesn't matter where this electric field comes from. This is the energy density of it. So although we determine this based upon what's inside by using our capacitor, it's true for any space. Any space that has an electric field contains this energy. So that's why it is so important, and that's why I wanted to make sure that we had a video about that.